In this video, we'll be solving exponential equations. I want to introduce a new property called the one-to-one property. It states if b to the x is equal to b to the y, then x equals y. So basically, if you can rewrite your equation with the same exponential base on each side, and there's only one term on each side, then you can simply set the exponents equal to each other. Our general strategy for solving exponential equations is first, you want to try to use the one-to-one property. It's the much easier route. If both sides can be written as exponentials with the same base, do that and apply the one-to-one property. Simply set the exponents equal to each other. This doesn't always work though, so our plan B is to rewrite our exponential equation in logarithmic form to get the variable out of the exponent and then solve the resulting equation. Let's solve the equation 2 to the x minus 1 equals 8. We'll find the exact answer and the estimate answer rounded to the nearest thousandth. Well, I have just one term equal to one term, so that lets me know that I should try the one-to-one property. In order to use the one-to-one property, I have to rewrite each side with the same exponential base. I clearly see the base of 2 on the left side, 2 raised to the x minus 1, so I want to try to rewrite 8 as 2 raised to some power. 8 is 2 raised to the third power, so I can rewrite the right-hand side as 2 raised to the third. I have the same exponential base on both sides, therefore I can use the one-to-one property and simply set the exponents equal to each other. Now we solve the resulting equation x minus 1 equals 3. We get x to be equal to 4. Next, we solve the equation 6 to the x equals 3 raised to the x plus 1 power. Again, I see one term on each side, so I'm going to try the one-to-one property. I need to rewrite both sides as either exponential base 6 or exponential base 3. So can we rewrite 6 as 3 raised to some power? We cannot. How about the other side? Can we rewrite 3 as 6 raised to some power? No, we can't do that either. So this is one where we have to try our plan B. We need to rewrite our exponential equation in logarithmic form. We do that by applying our definition, b to the y equals x is the same as log base b of x equal to y. We have two different exponential bases, so you can choose whether to rewrite this log base 6 or log base 3. In this example, there's one choice that's going to make the algebra that follows a lot easier. You always want to choose the exponential base that has more terms in the exponent. If there's a tie in the number of terms, well, then just pick one. But here we see that there are two terms on the exponential base 3, so that's the one we want to use. Our logarithmic rewrite is log base 3 of 6 to the x is equal to x plus 1. Now this helped us some. It got the x on the right out of the exponent, but notice that we have an x on the left still in the exponent and now inside the argument of a log as well. Oh, we need to gain access to that x. So we're going to use the property of logs that says that you can take the exponent out of the argument by making it a coefficient. This becomes x times log base 3 of 6 equals x plus 1. Well, this is great because now both of the x's are accessible, but notice that x shows up more than one time. Recall that anytime this happens, we want to get all the terms containing an x on one side of the equation and then factor that x out. So I'll subtract x over. We get x times log base 3 of 6 minus x equals 1. Please note that you can't, a common mistake that I see is when people subtract x from both sides, they think that these two x's here cancel out, and that is not the case. That x is attached to log base 3 of 6. So when you subtract the x from both sides, it's not a like term with that x times log base 3 of 6, so that's why it just has to go tacked on to the end. All right, now we have all the terms containing an x on one side, and we are going to factor the x out. This leaves us with x times log base 3 of 6 minus 1 equal to 1. Our last move to solve for x is to divide by this factor in the parentheses. Our exact answer is x equals 1 over log base 3 of 6 minus 1. That's our exact answer. However, our directions also asked us to get an approximate answer rounded to the nearest thousandth. Since our log is base 3 in our answer, we're going to have to use change of base formula to get the approximation. We're going to have x equals 1 over, now we'll do the change of base formula for the log base 3 of 6 portion. This becomes the natural log of 6 over the natural log of 3 minus 1. Make sure when you type this in parentheses that in your calculator that you have parentheses around the denominator. Typing this into our calculator and rounding to the nearest thousandth, we get x to be equal to 1.585. In our next example, we want to solve e to the 2x minus 4 e to the x minus 5 equals 0. Well, I know that I can't use the one-to-one property because I have more than two terms. There's no way that I can rewrite this as one term on each side. Well, this also rules out being able to just rewrite it in logarithmic form as is because I need to have just one term equal to one term. So that tells me I'm going to have to use some other kind of algebraic move. This is actually a quadratic trinomial in form. Recall that we know that this is quadratic because when written in descending order, our second exponent is half the first, and our last term is a constant. So we are going to factor this trinomial that is quadratic in form. You may choose to use substitution. I'm not in this instance. Factoring this, we get e to the x minus 5 times e to the x plus 1 equal to 0. We'll apply our zero product property and get e to the x minus 5 equals 0 and e to the x plus 1 equals 0. And then we solve each of these equations individually. E to the x minus 5, I should be able to solve this, if not by one-to-one property, as rewriting it as a log, since I only have two terms. We can rewrite this, e to the x equals 5. I have one term on each side. Well, I can't rewrite e as 5 raised to some number, and I can't rewrite 5 as e raised to some number. The one-to-one property is out, but I can rewrite this in logarithmic form. Our logarithmic rewrite is that the natural log of 5 is equal to x. And good for us, x is already solved for. There's our first exact solution. To get the decimal approximation, we can just type this in our calculator since it's natural log. Rounding to the nearest thousandth, we get x to be 1.609. Now we'll solve the other equation. We'll isolate the e to the x. I can't rewrite e as -1 raised to some power, nor can I rewrite -1 as e raised to some power. Therefore, we'll rewrite it in logarithmic form. We get the natural log of -1 is equal to x. Now, notice what's happening here in the argument of our natural log. We get an argument of -1. Recall that the argument of any log has to be positive. So this gets thrown out. This is an extraneous solution and it doesn't work for us. If you try to pop that in your calculator, you're going to get an error message. The only solution to this equation is that x equals the natural log of 5. Let's see an application problem. The population of a city is P equals 250,342 times e raised to the 0.012 t power, where t equals 0 represents the population in the year 2000. We want to find when the population will be 320,000. This 320,000 is our P. We'll substitute that into the given formula. 320,000 equals 250,342 times e raised to the 0.012 t power. Notice I have just one term on the left and one term on the right, even though that's an ugly term on the right. This tells us try one-to-one property or rewriting it as a log. To do either of those, I need to isolate the exponential base. So we need to isolate that e. We'll do so by dividing both sides by 250,342. When you try to divide these two numbers, you get a decimal that is not nice. We don't want to round our answer on the first step of solving an equation, so we're actually going to keep this fraction. You can simplify it if you like, but it's not necessary. Now that we've isolated the exponential on the right-hand side, there's no way we're rewriting e as that fraction to some power or rewriting that fraction as e raised to some power. So we are definitely going to rewrite this in logarithmic form. Our logarithmic rewrite is that the natural log of this big fraction is equal to our exponent, 0.012t. To solve for t, we'll divide both sides by 0.012. T equals the natural log of 320,000 over 250,342, all that divided by 0.012. Now we want to type that into our calculator. We get approximately 20.5. Anytime we have an application problem, after you solve, you want to go back, reread the problem, and make sure you've answered any question. The question is, find when the population will be 320,000. To say 20.5 doesn't make sense when they're asking us when. They're asking us for a year. We know that t equals the number of years after 2000. So if we go 20 and a half years after the year 2000, we'll be in the year 2021. A common mistake is that students want to tell me the answer is the year 2020. It is the year 2021 because we've already gone 20 whole years and now we're pushing halfway into the next year, which would be 2021.